Imagine a ball rolling down a smooth ramp. Its descent is continuous. Now, picture that same ball bouncing down a staircase. It doesn't glide, it snaps from one defined level to the next, with nothing in between. When we experience electricity in our daily lives, like feeling the zap of static after walking across a carpet, it feels exactly like that smooth ramp. We imagine static building up like water pouring steadily into a glass. But that fluid, continuous flow is a complete illusion. Electricity cannot take just any random value. Instead, it is delivered in strict, unbreakable packets. Physicists call this inherent graininess of the universe the quantization of charge. This invisible staircase governs both the static shocks we feel and the fundamental behavior of subatomic matter. The primary rule of charge quantization states that every free charge in existence is simply a multiplier of a single basic unit. This standard unit is universally represented by the lowercase letter e. English scientist Michael Faraday first suspected this discrete nature through his laws of electrolysis, but it was experimentally proven in 1912 by Robert Millikan using the intricate lab equipment you see here. In nature, there are exactly two subatomic particles that act as the physical carriers for this specific packet of charge, the electron and the proton. By convention, an electron carries the negative version, written as -e. A proton carries the exact same magnitude, but as a positive charge, +e. So whether you are looking at a tiny static spark or a massive lightning bolt, the entire event is dictated by the transfer of these specific, mathematically countable particles. This brings us to a very clean equation, Q equals NE. Here, Q stands for the total charge on an object. The letter E is that elementary charge packet we just defined, a fixed constant, and N represents the count of how many packets are present. Because you are counting physical particles, N can only be an integer, a whole number like 1, 2, or 3. You cannot slice an electron in half. Therefore, it is physically impossible to have 1.5 electrons, or any fractional amount of charge. This graphic illustrates exactly how small that base unit is. Measured in coulombs, the standard SI unit of charge, the value of E is 1.602192 times 10 to the negative 19th power. That infinitesimal number is the absolute bottom limit of the universe's accounting system. You simply cannot step down any lower. This presents a paradox. If charge is strictly quantized, why do engineers and physicists usually calculate everyday electricity as if it were a perfectly smooth, continuous value? The answer comes down entirely to the sheer difference in scale between a single electron and a standard unit like a coulomb. To accumulate just 1 coulomb of negative charge, you have to gather roughly 6 quintillion electrons. That's a 6 followed by 18 zeros. Even in small everyday situations, like dealing with static cling measured in microcoulombs, we are still interacting with trillions of discrete charge packets all at once. Look at this simple dotted line. Up close, the massive empty gaps between dots are obvious. But as we pull perspective back, the gaps completely vanish. To the human eye, the sequence blurs into a perfectly solid stroke. The exact same thing happens with electrical charge. At the macroscopic level, adding or removing 1 electron from an object is a step so unbelievably tiny that the grainy, stepped nature of the charge is completely lost to us. Treating electricity as a continuous fluid is a useful shortcut for large-scale engineering. But at the microscopic level, charge remains strictly divided into these indivisible lumps.